So I'm going to explain point number 6, deduce the E0 values of the relative reactivity of the element, compounds and ions as an oxidizing agent or as a reducing agent. Then point number 8, not 7, basically because we have discussed it in I have explained it in my previous lectures that how to make an overall equation or how to make a redox equation by combination of two half equation, and how to make overall equation with the help of two oxidation and reduction half equation. So once again, if I'm having any sort of example, then I will let you know just for the sake of practice. There is a point number 8, predict qualitatively how the value of the electrode potential E varies with the concentration of the ions. Yes, it is very much important, and usually it is asked in every year questions. And point 9, then we use the Nernst equation. That is, there is a Nernst equation, and this is a simplified form of the Nernst equation, that by changing the concentration, how much value of the E0 has been changed or that is going to change with the typical example. And the last one is how delta G is related with the E0 of the cell, or how E0 of the cell is going to be diagnosed. I will try my level best to explain the last point as well today. First of all, I'm going to once again talk about how to see, how to check the E0 value of the different element, and how can we decide which one element is an oxidizing agent or which one is the reducing agent. Number one. Number two, which one ion or which one element is stronger oxidizing agent comparatively, and which one is the weaker reducing agent or oxidizing agent, etc., etc. So for example, I'm going to starting from the data booklet, you can see my screen that there are different equations. These all equations are called half cell equations. These all equations are also known as half cells, or they are called electrodes. So in each half cell, in one half cell, this is the one half cell, this is second half cell, third, fourth, fifth, seventh. So in each half cell, basically, we are going to connect two different oxidation state of same element. So in all half cells, we connect two different oxidation state of the same element. So just have a look. In this case, they all are almost same in terms of electrons. In all these cases, in all these equations, basically electrons are lying on the left hand side of the equation. In all type of reaction present in the data booklet, in all type of reaction, you will see that even it is given in the question paper or it's given in the data booklet. So the standard way is to write the equation with respect to reduction potential. So basically this is the reduction potential. All these equations are reported in data booklet or will be reported in your question paper like a reduction potential values. So the species present on the left hand side are said to be oxidizing agents, number one. And species present on the right hand side, they will be reducing agent. It's fact, it's true, and it's always true. It's been always true. It will be true whenever you are going to examine an equation. So the species that is present on the left hand side is oxidizing or will be oxidizing agent, and the species, any element, any compound, any ion, if they are present on the right hand side of the equation, they are reducing agent. So this is the first step of this lecture, or the main theme of this lecture, that point. So the second one thing is, you can see that in second equation, aluminium 3 positive ion, again it will be oxidizing agent. And what about aluminium? it is reducing agent. Same is the case, barium 2 positive ion, oxidizing agent, barium itself, pure barium, reducing agent. 2Br negative ion, reducing agent, and Br2, original bromine, halogen, is oxidizing agent. Calcium reducing agent and calcium ion oxidizing agent, and so on. Now the next question is, which one is, for example, I'm going to compare silver ion and barium ion. Which one positive ion, they both are oxidizing agent, which one positive ion is behaving, or that is a strong oxidizing agent. To see the strength of the oxidizing agent, just straightforward, you will check, you will compare these values. What is the definition of oxidizing agent? Oxidizing agent is a species that accepts electron. The power of Ag positive ion to accept electron is plus 0.80. The power of barium 2 positive ion to accept electron is minus 2.90. So it means that the barium 2 positive ion has negative power to gain the electron. Silver positive ion has positive power to gain the electron. So the species that is having more power to gain the electron is strong oxidizing agent. So Ag positive ion is more powerful oxidizing agent, strong oxidizing agent than barium 2 positive ion. It means that it is concluded that from this sort of data. Now at the same time, I am going to compare silver pure metal and barium pure metal. I mean, they both are reducing agent. We know which one is the stronger reducing agent. What is the reducing agent? Any species, any element, any ion, any atom that loses electron. If I'm going in a reverse way, just concentrate on the reverse reaction, the bottom arrow I mean. So if they are losing electron, then which one is having more capability to lose electron? For this sake, to check the capability, as the reaction is moving in reverse direction at the moment, so I am going to invert these values. So this value will be minus 0.80. This is called its oxidation potential. And same is the case, S value will also be reversed because this reaction is going to move in a reverse way. It will be plus 2.90 volts. Now in this comparison, barium is winner. Barium can lose electron with the more power, with a plus 2.9 voltage power. But silver cannot lose electron by itself. It is having negative potential to lose electron. So anybody that want to gain the electron from the silver, I mean, it will have to snatch the electron from the silver. It's not going to lose electron happily. So barium metal is more reactive than silver metal as far as their reducing power is concerned. So barium metal is stronger reducing agent than silver metal. So on behalf of data booklet, by watching the calculation reactions, by watching these scheme, these equations, you can predict actually the nature of oxidizing and reducing agent. Now the next point that was over there, that how concentration may affect the value of E naught. Two things can change the value, these values. Only two factors mean, two things mean two factors. Only two factors can change these value of E naught. And then these value are not said to be E naught they are called general or specific electrode potential. E naught mean standard electrode potential. Electrode potential at 298 Kelvin at 1 mole per dm cube concentration. If you are using any gas, then 1 atm pressure of the gas is over here, or the gas is passing at 1 atm pressure. But if you are changing any one of the condition, if you are changing the temperature, if you are going to use it at 100 degrees Celsius, for example, if you are going to operate it 90 degree, 100 and so on, then this condition is not standard condition. Number two, if you are changing the concentration of any ion, because concentration of solid metals, pure element cannot be changed. Especially solid, the concentration of liquid element and the concentration of solid elements cannot be changed. So wherever is the ion or the gaseous species are there, you can change its concentration. By changing the concentration, this value will also be changed. Yes, it is true. Then again, it is not known as standard electrode potential. Now come to the next one. In next thing, if I am going to change the concentration, if the concentration is going to change, then this value will no more be the E naught value. Let's suppose you can increase or double the concentration, or you can decrease to the half concentration. You can change the concentration. So after changing the concentration, number one, this answer will be changed. How much will be this answer? We cannot predict it in a simplified way. We cannot predict it by the normal mathematical equations. For that purpose, we will have to use Nernst equation. So first thing, that how to check the change in concentration effect. Just have a look. Once again, I am going to add more silver ion into this box. This box means this is a half cell. Here is a half cell, and here is Ag positive ion, and here is silver ion, silver metal, and at the moment it is equal to 1 mole per dm cube, and its electrode potential is potential to gain and lose electron with respect to She is plus 0.80. But if I'm going to reduce this concentration, let's suppose, if I'm going to make it half, most of the silver compounds are not very much soluble in water. So sometimes they show in the question that some of the solid is settling down over here. Or sometimes they said that it is saturated solution. So this thing indicate, saturated solution indicates that this concentration is not equal to 1 mole per dm cube. This is the indication. The second thing is this one, as it has settled down, some of the undissolved species or undissolved compound is also present in the beaker. Again, it indicates that this compound is not fully soluble. And if it is not fully soluble, simply it means it is not 1 mole per dm cube. This is a KAC tip and trick, you can say. So if I'm going to decrease the concentration to the half mole per dm cube, or I have decreased, then what will happen to this value? So how to think about it, and how to make your answer, how to develop your concept, or how to justify answer or the values. Simply, how to predict at least what will be the new value. Either the new value will be higher or lower, you can easily predict. So just have a look. This beaker is having 1 mole per dm cube silver ion, right? If I'm going to decrease this concentration from 1 to half, So this is a sign of reversibility. This is a reversible reaction. Upon decrease in concentration of Ag positive ion, let's suppose it was initially 1 mole per dm cube, and I have decreased it to the half concentration. So what will happen? Equilibrium will be shifted towards the left hand side. I mean, the position of equilibrium will start to move, will be shifted towards backward. They will move towards backward to make more and more and more silver ion, to compensate the silver ion. So whenever the equilibrium is going to shift, or during the shifting of this position of equilibrium, POE, is going to shift towards the backward, it means that the concentration of silver is going to decrease, and simply this answer will also decrease. But we cannot predict that how much it will decrease. As I told you, for the exact value of its lower value, we will have to use Nernst equation. So, reversibly speaking, if I am going to add more silver ion into this beaker, so there is more concentration of silver ion. To reduce the concentration of this silver ion, equilibrium will be shifted towards right hand side. So if equilibrium is shifting towards right hand side, this value will increase, this worth will increase. Or if the equilibrium is shifting towards the backward side, its value will be decreased. So this is the basic theme, and you will always use original data booklet equation. Sometimes equations are given in a reverse way. For example, let's suppose examiner told you that this is the equation at the moment. He is using this equation in that question. And he is asking that I have decreased the concentration of silver positive ion, and what will happen to the E naught of the cell. So simply it means you will not consider this equation. Your answer should be on behalf of this equation. And this equation will definitely be given in the question. Or you can also revert this equation. So electron must be on the right hand side. Left hand side. Whenever you are going to write this equation. Silver positive ion plus 1 mole of electron goes to silver. So you will rewrite this equation. Now you will announce your prediction. If you are going to decrease the concentration of Ag positive ion, equilibrium will be shifted back, so E naught will be decreased. According to this equation, the answer will be reversed, and that answer, in my opinion, as far as my experience is concerned, as far as the different old marking schemes are concerned, the answer will be wrong. All answers are made on behalf of this pattern. If this pattern is not given to you, change the pattern and then apply the rule, and then find the E naught, new E naught. I mean not new, new E value of that electrode. Same is the case if you are having overall reaction. For example, I am having an overall reaction of let's suppose H2 and this one. For example, Fe2 positive ion and 2 mole of Fe2 positive ion plus 2 mole of H positive ion. I'm going to write let's suppose, and here is the formation of H2 plus 2 mole of Fe3 positive ion. Now if he is asking, then what will happen if I am going to decrease the concentration of H positive ion? I am going to decrease the concentration of H positive ion. Then overall E cell, this is E cell, this is not the E electrode. The above one that I told you, that I explained you, that is E electrode. Just one answer of single half cell, of single beaker potential. That was alone one electrode potential. But this is not alone. This is the answer of whole E naught of the cell that has been changed, that is going to change. So if H positive ion is going to decrease, so what will happen to E cell? obviously the whole reaction is going to move in a reverse direction now. Now you can take this equation. Yes, it is true. There is no need to there is no need to consult the data booklet now. Just consult this equation. Simple. It will be correct. I mean, answer will be correct. So again, just see the direction of position of equilibrium. If it is shifting back, obviously E naught cell will decrease. Its worth will decrease. If, for instance, if it is negative, initially it is negative 1.0, then after any change in concentration, the position of equilibrium is shifting towards backward, then it will be minus 1.20. Its worth will be decreased. Worth, it's I mean, in negative this number is going to increase, overall its worth is going to decrease. If this is moving in right hand side direction, so in this case obviously its worth will increase, mean it may be minus 0.7. So if the equilibrium is shifting towards the right hand side, answer's worth will increase. If the equilibrium is shifting towards backward, toward the left hand side, then worth of the answer will decrease. So this is the basic main theme to check the effect of concentration of any species that is present at the stage of dynamic equilibrium. Look, there is a new aspect of oxidizing agent in one equation. Does it react with reducing agent in another equation? This is the question. So usually it is believed that every time any oxidizing agent is going to react with any reducing agent. But it's not true. Because some oxidizing agent does not react with the reducing agent. For example, just have a look in this equation. And I'm going to highlight it over here. In this case, in this equation, this cobalt is oxidizing agent, and the answer of its nature of oxidizing agent is minus 0.28. I mean, its oxidizing power is negative. In this equation, CO2 positive ion, cobalt 2 positive ion is acting as reducing agent. Here it was oxidizing agent. So does these two oxidizing and reducing agent will react? The answer is very simple. What is the answer of power of value of this reducing agent? I mean, power of reducing power of CO2 positive ion will be negative, because we are going to move in a reverse way. So I want to check this answer. CO2 positive goes to CO3 positive ion plus loss of electron, and its answer will be minus 1.82. So this is reducing agent power answer. This is the answer of oxidizing agent and its power. And if this answer is bigger than this one, then reaction will happen. And it is not bigger, it is less than that of, so they cannot react themselves. I mean, cobalt 2 positive ion, when it's acting as an oxidizing agent, it cannot another cobalt 2 positive ion that is acting as reducing agent. So this reaction won't happen. So these, after the mixing of these two half cell, there will be no reaction. Now come towards another option. In this equation, this is oxidizing agent, and in the next equation, or any other equation you can say, this is acting as reducing agent. So again, the question is, will these two react with each other or not? Here is the answer of this is oxidizing agent, and its electron capturing power is minus 0.34. And what is the answer of its reducing nature, its reducing power? That is, I mean, positive 0.91. I have to flip this equation because as these two are the reactant, now it is going to react with a simple chromium. So I will have to flip this equation, and chromium goes to chromium 2 positive ion plus 2 electron, and answer is positive. Now once again you will compare these two answers. If the answer of the reducing agent, if the power of the reducing agent is higher than the power of oxidizing agent, then reaction will happen. And yes, it will happen when you are going to mix these two species, especially, whenever you are going to mix this cobalt hexa amino cobalt ion and simple chromium in a beaker. In a beaker, if there is chromium metal and you are adding this complex CO NH3 6 cobalt 2 complex, then yes, reaction will happen, and finally what will form? There will be the formation of chromium 2 positive ion, cobalt metal is formed, ammonia is formed. So reaction will happen because the answer of the reducing agent or the power of the reducing agent is more, is higher, is greater, is bigger than the power of this oxidizing agent. So this is, you can say, a Kaiser rule. Then whenever you are going to check the two reaction between oxidizing and reducing agent, then just check their answer. If the answer of the reducing agent is bigger, is more, is higher than that of answer of oxidizing agent, the value of oxidizing agent, then reaction will happen, then the reaction will be feasible, and that reaction will be spontaneous, yes, you can say. But if the answer of the reducing agent is less than that of the answer of oxidizing agent, then reaction will not happen. This is the shortcut, and that is very useful in my opinion. Now, the next thing is, if they are asking to find the new answer of E cell or E naught of the cell, then how will you find it? Definitely, as I told you, that we will have to use Nernst equation, and I'm going to explain this phenomena over here. Nernst equation. This is the simplified form of Nernst equation. This Nernst equation is used at 298 Kelvin. That is basically a room temperature. If the temperature is changed, then this equation will no longer valid. That is another full form equation that is also given in my book, but usually this is used, and it is supposed that we are operating at 298 Kelvin. E, new E of the electrode, simple single electrode is E, and this is the value of E naught, original E naught. 0.059 is a constant number, Z is the mole of electron, log is in the formula, oxidized species divided by reduced species. For example, as two equations are given over here, so I'm going to include the example of copper over here. What is the answer of this half cell? If the half cell is having Cu2 positive ion and Cu rod, copper rod into it, this is called one half cell, and its equation is over here. So I am going to write its equation once again, and its E naught is equal to E naught, means standard answer is plus 0.34 volt. At that time, its concentration is 1 mole per dm cube. If I'm going to decrease its concentration to half, for example, then what will be its new answer? Obviously, if its concentration is going to decrease, equilibrium will be shifted towards backward, and its answer will be decreased. But up to how much extent we cannot predict without this Nernst equation. Now, what is the Nernst equation? How to use this equation to find the new answer? E is equal to E naught, original answer, plus 0.34 and plus 0.059 divided by Z. Z is the mole of electron exchanged during this reaction with respect to 1 mole concentration, that is equal to 2 plus, into log, I'm going to erase it at the moment, into log of, which one is the oxidized form in this whole box, that is copper 2 positive ion, and now it has been half, its concentration is half, and it is a solid, and for solid the concentration is always taken 1. Now what is the new answer of this equation? That is the new electrode potential of this half cell. This is just one cell new potential and I'm trying to solve it. Plus 0.34 plus
0.33, I believe.
Plus 0.33?
33. Yeah,
okay.
Pretty sure it's 33.
Good. So now just have a look. If you are going to decrease the concentration up to half, I think you have noticed that if the concentration is decreased to half, it is very much huge change in concentration. Half of the concentration has been changed, but the answer is slightly changed, just change up to 0.01 value. Yes, it is decreased. We can predict accurately that whether it is going to decrease or increase, but we cannot predict that how much quantity is going to be decreased or increased. Same is the case in this case. For example, I'm taking a beaker in which I am going to use the 2 concentration of iron 3 positive ion, and iron 2 positive ion. Both concentration I am taking 0.1. Let's suppose. Let's see what is the answer in this case. And I'm going to use direct formula. What is the E naught? If I'm not wrong, it is 0.77. Let me check it. 41. Iron 2 to iron 3, 0.77, yes. So 0.77. 0.77 is the standard electrode potential plus 0.059, that is in the formula, divided by 1. Here this time I'm going to use 1, not 2, because there was 2, I used 2 over here, but now there is 1, I'm using 1. Log into, what is the concentration of, both concentration I have taken same, 0.1, 0.5 over 0.5. So that's 1. What will be the answer of this E naught if the concentration of both species are taken same? What is the answer?
$0.77 plus 0.77.
Correct. If you are, this is the new phenomena. If you are taking the same concentration in this case, not in this case, because there is a solid and one is aqueous. If the both species are aqueous and you are taking the same concentration, even you have reduced the concentration of the both, not the one, then answer will remain same. Answer will not be changed. But if I'm taking, I'm just reducing the one concentration of Fe2 to half and Fe3 is equal to 1, then what will be the answer? Oxidized form is equal to 1 and reduced form is equal to half. So let me know what will be the answer. If I'm going to reduce the answer of Fe2, so E naught will increase, because in this case equilibrium will be shifted towards right hand side. So what will be the new answer if the concentrations are not equal? And plus 0.77, sorry for my this pen.
0.78 plus
The new answer is
0.78.
0.78, so slightly increase, yes. So now we have learned two things. If the both side of the species are aqueous and they are having the same concentration, or they have increased by the same concentration, or they have decreased by the same concentration, then their electrode potential will not be changed. If they are not decreased with the same magnitude, then definitely there will be change in the E naught value. And again, we will use this Nernst equation to find the new answer. But if the one of the species or one of the element is pure element, if it is solid or the liquid state, then there will be definitely change in the answer of E naught. I mean, whatsoever is the new concentration, either it is higher or lower, then the new answer will be changed, as we have seen in this case. But if the two species are present and both are aqueous, they are constituting a half cell. And if we are going to decrease or increase the both concentration by the same way, then there will be no change. Same is the case if I'm going to add anything else that is going to affect the equation. For example, I'm going to write once again another equation. For example, Ag positive ion, or I'm using, where it is, there is one thing more. Ag positive ion plus it's going to react with Fe3 positive ion to make Ag plus Fe2 positive. So I think I will have to multiply it. Which one is having the more answer? So sorry, it will be flipped. I mean, there will be 2 positive and there will be 3 positive. No, this is the correct, balanced equation. Now, if I'm adding Cl negative ion into this beaker, so in this reaction, silver 1 positive ion, Fe2 positive ion, and again you will draw reversible arrow over here to goes to Ag and Fe3 positive ion. Now let's see over here, if Cl negative ion, if I'm going to add Cl negative ion, or I'm going to add NaCl solution into this beaker. So you know, Cl negative ion will react with Ag positive ion to make AgCl, and it's a solid. So this Cl will decrease the concentration of Ag positive ion. But if it's going to react with Fe2 positive ion, Cl, or if it is going to react with Fe3 positive ion, Cl negative ion. So in both cases, FeCl2 or FeCl3, they both are water soluble. So there is no change in the solubility. There is no change in the solubility. I mean, each Cl is having one negative ion in both cases. So they will remain unchanged. There will be no change in concentration because of the solubility of the species. But the concentration of Ag positive ion will be disturbed because of addition of Cl negative ion. So overall, what will happen? There will be the deficiency of Ag positive ion. Equilibrium mixture will start to move towards left hand side. Position of equilibrium will move towards left hand side to overcome the concentration, lost concentration of Ag positive ion, and overall E naught will decrease. Overall E naught will decrease. Now, if any case, if I'm going to add any other component that is not going to make precipitate with anyone. Let's suppose I'm going to add nitrate ion, sodium nitrate, in form of sodium nitrate. So sodium nitrate is not going to change the concentration of any ion present in this beaker, in this whole mixture, because all nitrate are soluble. So Ag nitrate is soluble, Fe2 nitrate is soluble, Fe3 nitrate is also soluble. So this nitrate is not going to change the composition of the mixture, so it will not change the E naught value. So it will not change the E naught value. So as far as the basic, effect of concentration on the whole equation or the overall equation is concerned, you will check in this way. Now I am going to solve some questions regarding this topic as far as my opinion is concerned, especially this is the question paper, May-June 24, and it's a 4-2 variant, and its question number is 2. Question number is equal to 2, part C, and this is a technical question or typical question, you can say. Just have a look. Here is, the table. 2.1 is the table, data booklet. In other words, you can say this is the data booklet, given data booklet. Shows electrode potential for some electrode reaction involving manganese compound. And here is the question. Aqueous magnate 6 ions is a 6, 5 plus 1, 6 ion, are unstable in acidic condition and undergo disproportionation reaction. The E naught of the cell for this reaction, which one is this one, or any possible reaction that is going to happen, that is going to destabilize, to decompose, you can say, this one negative ion. For that reaction, E naught of the cell is equal to 1 plus 1.14 volt. He is asking to construct an ionic equation for this disproportionation reaction. Now, this is a tricky question. Basically, just have a look. In this case, as he said, and we know, the oxidation state of Mn is equal to plus 7. What are the disproportionation reactions? Reactions in which the same species, the same element sometime, same component is going to, same molecule is going to oxidize at one place, and as well as it is going to reduce itself in other place. It is going to change its oxidation number more than 6. It may be 7 positive, it may be 8 positive, etc., etc. For example, and it may change its oxygen state plus 5, plus 4, plus 3, plus 2, etc. So in a same reaction, in a single reaction, if a species is going to change its oxidation state in opposite direction, initially it is having plus 6 oxidation state, finally at one place it is going to raise its oxidation state, it may be plus 7, and manganese can show maximum plus 7, not plus 8, and it may decrease to 0 even, and plus 4, plus 5, plus 3, plus 2, plus 1, and so on. So any one of the possible oxidation state is over here. And whenever you are going to add two equations, obviously one will be the oxidation equation and other will be the reduction equation. And whenever you are going to add these two equations, the overall answer of the E naught must be equal to plus 1.14. So first thing is we need acidic conditions. He is asking to use acidic conditions. It is unstable in acidic condition. Just have a look, where are the acidic condition? Here is the acidic condition. Right. Here is the acidic condition. I'm sorry. acidic condition, acidic conditions, acidic conditions, no, alkaline condition, and acidic condition. So I have shortlisted basically 4 equations to make my answer, to develop my answer basically. Now, the starting point is this one, MnO4 2 negative. Where is MnO4 2 negative? Here is MnO4 2 negative. Here is MnO4 2 negative, but sorry, this is not the acidic equation. And the next thing is MnO4 2 negative. Here is the MnO4 2 negative. And any other equation in which there is MnO4 2 negative? No, there is no MnO4 2 negative, and so on. So basically, I need this MnO4 2 negative on the side of the reactant. This is the basic theme. This is the basic clue of this reaction, because there is one reactant, one major reactant, that is MnO4 2 negative ion. The second reactant is H positive ion, because it has said that there is an acidic condition. So basic reactant, whenever you are going to use any 2 equations and you are going to add them out, so the overall answer will be having MnO4 2 negative ion on left hand side of the equation. Next thing is, if I am going to use this equation, what is happening in this equation? What has the new oxidation state of Mn2 positive? It's plus 4. So initially it was plus 6 and now it has been changed into plus 4. So yes, number 1, it has been reduced. So this is called reduction equation of MnO4. In this half equation, Mn6 positive ion is going to reduce. Correct. Fine. In the next equation, there must be MnO4, and here it is. And what is happening? Here is a plus 1. Here is plus 7. MnO4, 1 negative ion. In this case, its answer is plus 7. And oxygen is minus 8, or 8 minus. And sum is equal to 1 minus. So what is happening in this case? It is going to oxidize. It is going to oxidize. So yes, in this equation it is going to reduce. In this equation it is going to oxidize. And I will have to flip this equation. I will have to flip, because I have to make this reactant. So to make MnO4 2 negative ion as a reactant species, I will rewrite this equation. MnO4 2 negative goes to reversible arrow to make MnO4 1 negative plus 1 mole of electron. And as I have flipped the equation, so its answer will also be flipped. Now, to check that either I have selected correct or incorrect equations, so this is the one answer, this is the second answer. I'm going to add them. I'm going to add these 2 numbers. So plus 1.70 and minus 0.56. What is the answer? Is it plus 1.14? And yes, it is. So yes, I have chosen the correct equations. One is this equation, other one is this equation. So that was the trick in this case. First of all, I checked that it's a disproportionation reaction. Then I checked the conditions are acidic, and according to this reaction, this should oxidize. Same MnO4 should oxidize in one equation, and it should reduce in another equation. Then I have to add these 2 equations to make the answer, or sum should be equal to 1.1 volt. So what is the overall equation now? I'm going to write the first equation, then second equation. Here are 2 mole of electron. The second principle to write overall ionic equation is to balance the electron. So I'm going to multiply it by 2, 2, 2. If you are going to multiply all the species by any number, by 2, by 3, by 4, then this answer will not change. Once again, if you are multiplying any number to the whole species in the equation, to each and every species in the equation, then the answer E naught will not be changed. It will remain same. So what will be the equation? This one, 2MnO4, I mean this one. So 2MnO4, 2 negative goes to 2MnO4, 1 negative plus 2 electron. The second equation is I'm using as such, that MnO4, 2 negative goes to, I'm sorry, plus 2H, 4H positive ion and 2 electrons goes to MnO2 plus 2 mole of H2O. Now, I'm going to add these two equations. Electrons will be cancelled out and nothing is going to be cancelled out further. So 2 mole of MnO4, 1 mole of MnO4, 2 negative ion, they will be, become 3 mole. So 3 mole of MnO4, 1 negative plus 4 mole of H positive on the left hand side. What is on the right hand side? 2 mole of MnO4, 1 negative plus MnO2 plus 2 mole of H2O. This is the correct option as far as my knowledge is concerned, or my calculation is concerned, and overall is this one. The next one, suggest and explain how the E cell value of the disproportionation reaction changes with increase in pH. Now he is saying that if I'm going to increase the pH, then how much this E naught of E cell, that is not E naught. E naught is when the concentration is taken 1 mole per dm cube. So if I'm going to change the increase in pH mean there is alkalinity. I mean that I'm adding or increasing more OH negative ion. So what will happen? They will neutralize H positive ion. So what will happen finally? Equilibrium will be shifted towards backward. As because of OH negative ion, H positive ion concentration will decrease. So position of equilibrium will be shifted towards left hand side, and as a result E naught will decrease. E cell will be decreased. It will be lower, and because position of equilibrium, you will write the complete words, will be shifted towards left hand side as pH increases, and so on. That was all about this today's lecture. Thank you very much.